Thank you for being here. My name is Jesús Perales Díaz. I'm working under the supervision of Eduardo Aedo and Adrián Domínguez. And my work is on fluid kinetic models for space plasma thrusters. So these are the contents, the list of contents of my talk of today. I will really go really fast through the motivation, research gap, and also I will provide a brief summary of my previous work. And then I will jump straight into results, and I will finalize with some academic achievements and my future work. So as a general motivation for exploring and understanding plasma thrusters, well, the main motivation for using them is high specific impulse as compared to the conventional chemical propulsion systems. This high specific impulse allows us to reduce significantly the propellant consumption. So, well, there is a penalty in the low thrust that we achieve with these thrusters, which is basically a limitation due to more electric power. But the huge advantage of low propellant consumption makes this technology the present and future of space propulsion. Now, in my thesis, I've been focusing on the study of gridded ion thrusters, the one on the left, and a Hall effect thruster, the one on the right. Mainly on Hall effect thrusters, you'll see it now. These are like very consolidated technologies, but still there are parts of the physics of these thrusters that is not well understood. And also in the design of this thruster, we are still highly dependent on experimental measurements and testing, which are really costing activities. For this reason, it is required to develop numerical tools that are predictable and allows us to simplify these, to solve these these gaps that I've just mentioned. So this is the main focus of my thesis, improving an existing numerical simulation tool, which is Hyphen, that has been developed by the EP2 group, which is a hybrid particle in cell fluid code. You've already learned about these things in previous talks. And I also focus on the simulation of real prototypes to better understand the physics of these prototypes and help in the design process. So I just present here a summary of my previous work. I worked initially with a code of the group, which is called EP2+. You've already heard of during previous talks. And I started some problems related to gridded ion thrusters. I published a journal article on this. Then I proceeded to upgrade Hyphen for simulations of novel Hall effect thrusters featuring magnetic shieldings of the thruster walls. We call this thruster MS Hall effect thrusters. And then I started simulating real prototypes within H2020 projects in these frameworks. I started simulating a 5 kilovolt thruster, which is the HT5K thruster. I published an article on this. And then I started the simulations of another real prototype, which is the 20 kilovolt Hall effect thruster called HT20K. So what's new? What have I done during this last year? Well, I continued the studies of the voltage simulation of the HT5K thruster. So what is this voltage modulation? Let me tell you first that you need to know that Hall effect thrusters, the stationary discharge of these thrusters is not steady. It's highly dependent on time. There are a lot of oscillations. There is one that is particularly important, which is called breathing mode oscillations, which is a large-scale, relatively low frequency oscillation. And the existence of these breathing mode oscillations is problematic because of electric interference with other circuits of the satellite and for other reasons. This is why we want to somehow control this breathing mode, this oscillation, even damp it. For this reason, we modulate the discharge voltage. The discharge voltage is the voltage that is set between the anode and the cathode. You can see it here in this scheme in this simplified scheme of a Hall effect thruster. So we have run simulations of this voltage modulation of a real Hall effect thruster, actually, of the HT5K1. And we found, and we've proved with our simulations that we can indeed control the breathing mode oscillations. And this leads to electromagnetic interference mitigation, and also it can help in improving the diagnostics in Hall effect thrusters. We have also been able to identify which is the main mechanism by which we are able to control the discharge oscillations by means of this voltage modulation. And this mechanism is the control of electron temperature. You actually can see this here. I'm not going to enter into the discussion of this figure, but you can ask me if you want later. Also, by using data-driven techniques that have been used previously, like Madaloni et al. Already used it in Hall effect thrusters, in particular one which is called HODMD, we have been able to isolate the modes that exist in the discharge, and we have been able to isolate the driven breathing mode. And you can actually see here the amplitude of the different plasma properties of the mode, of this particular mode, the driven breathing mode. You can see the amplitude of the mode in the different, well, inside the chamber of the Hall effect thruster. Then I continued my work on simulating real prototypes. In this case, high power prototype, which is the HT20K, which is also magnetic shielding prototype. And well, I've proceeded to characterize fully this thruster. I've studied the breathing mode, plasma wall interactions, and some plume effects, like check ions, background pressure effects, stray currents. So I've just shown here like two pieces of this, two small pieces of this investigation, of this research. First of all, on the right, you can see what is the effect of the existence of check ions. What are check ions? Well, these are very slow ions that are created in the plume by a particular type of collision. And the problem is that these ions increase erosion of the Hall effect thruster. Actually, here you can see how we were able to find with our code and backward current of these slow ions that is impinging on the thruster walls and is therefore increasing erosion. Also, I started with hyphen. We were able to study which is the effect from shifting from the usual propellant type, which is xenon, to krypton, which is an alternative for xenon, which is cheaper and more abundant. We were able to identify the causes for the decrease in the performance related with the usage of krypton, and we were also able to see, and this is what we are seeing here in this comparison of pictures, we were able to see the worsening of the magnetic shielding. So magnetic shielding wants to keep a very low temperature of electrons near the walls of the thruster to reduce erosion. And actually here we are seeing that there is an increase, a slight but an increase of temperature when we move from xenon to krypton. So there is a worsening of the magnetic shielding. We are also able to analyze this with hyphen. Then my research took place from September to November last year. And I went to Imperial College to, participate in the modeling and testing of experimental, of a new prototype, which is called wet head thruster, which is run with water as propellant. In reality, a water electrolysis product. I'll discuss that later. And we wanted to prove that it's feasible to operate with water. So, and this is an alternative, a feasible alternative to the usual propellants, say xenon, krypton. So first of all, I participated in the improvement of the existing code there, which is in Imperial College, which is PlasmaSim. The goal is to identify the sources of inefficiencies associated to water, which we of course expect to be many, and to look for potential improvements in the design. This is still an ongoing work. You are seeing here a preliminary simulation, and I just wanted to show it to you what is the type of simulation we run. And then the second part of my stage, the last month, practically, was focused on experimental activities on this real prototype we were trying to simulate. Now we're actually testing it in the vacuum chamber of Imperial College. So for the first time, we were able to prove a stable operation with water electrolysis products, and this was already a huge achievement. We, of course, came across many problems because this was completely new for us. There was a really quick oxidation of the anode because the environment was really not friendly for the metallic surfaces of the thruster. We also observed passivation of the cathode surface, which was also completely unexpected. And well, here you have actually the moment in which we were able to, for the first time, ignite the thruster. So now you see what comes next is the first ignition of the thruster with the water electrolysis products. Finally, the measured efficiency was acceptable, was of course low, much lower than with xenon, but was deemed acceptable by ESA. And indeed, the experimental campaign continued at ESA facilities. And well, I'm just finalizing here. This is a summary of all my academic achievements so far. And well, regarding my future work, I will be preparing hopefully 1 or 2 papers on the ongoing research activities, and I will try to finish writing my thesis during this year. So that's all. Thank you. If you have any question, I'll be glad to answer.